my God.
Construction. As part of the River Valley excavation, we're going to be removing, treating, and reusing close to 1.5 million cubic meters of contaminated soils in line with the new soil regulations, which treat soil as a resource rather than a waste product. We'll be fully sealing the new river valley from the lake and groundwater systems to construct all of the river and its finishes in the dry. And we'll be creating new wetlands and other complex aquatic habitats for all of the marine life present in the area. So once the new river valley has been completed, we will have, sorry Fitzgerald, maybe we can just put a pause and go back. I know I threw you off there. Once the new river valley has been completed, we'll have created an island that you can see there in the graphic. So we're going to need to create a way to get on and off that island. And that leads us to the topic of today's discussion. As part of the project, there are 4 new steel bridges located at 3 sites. At site O and R in pink there, we have the Cherry Street North twin bridges. One is for vehicular traffic and one is for LRT or future transit traffic. We have Cherry Street South at location P, which is a vehicular bridge. And at Q, we have the Commissioner Street Bridge. Also, as part of this project, we're doing a replacement of the existing Lakeshore Bridge, but that will follow a more traditional construction approach and won't be touched on by today's discussion. So where are we now? Well, we've completed the delivery of the first steel superstructure for the LRT bridge. We're going to focus on that today. The rest of the team is going to touch a little bit on the fabrication, delivery, construction process. But I think it's important to note, before we get going, just to provide a little context, that the steel superstructure is being fabricated entirely offsite in Dartmouth, Nova Scotia. I'll leave it to Blair to discuss the reasoning behind this decision from the fabricator perspective. But as you can imagine, that brings in itself a whole host of challenges that we had to deal with. So before I hand things over to Mike Machino at Intuitive, I'd like to just show a quick video of the arrival and the installation of the first of the Cherry Street North bridges, because I think it provides an excellent context for the rest of the discussion. So Fitzgerald, if you could flip the next slide and hit the video, and then once the video finishes, we'll turn it over to Mike. So as you can see, the bridge was barged in. We've actually set it from the barge onto its bearings. My fellow presenters will get into this in more detail.
Okay, thanks for that, Matt. So I'm going to take you now through some of the design aspects, particularly how we arrived at the form that we have right now, some of the thinking of the design team. Next slide. So when we started the job, Waterfront Toronto gave us the mandate of designing a family of bridges for the city of the future. So what does that mean? Well, the family of bridges relates to the 3 sites. They wanted them all to relate to each other and to sort of frame what is this new community that's being built out in the Portlands. And the nature of that community is going to be, very modern, high emphasis on technology, a lot of prominence to pedestrians and cyclists, and of course linking to the park, adjacent park, and to the community. And so with that context, the design team took that and said, okay, well, our response to that was really, let's look at a shell. Oh, sorry, just back up. Yeah, let's look at a shell structure. We like the shell structure because of the simplicity and elegance of the form. And the idea was to then take that shell and start to remove material that really wasn't primary to the structural force flow. So to remove material that was not really necessary to carry the forces of the structure. And then in addition to that, because it was a shell, we had to pay a lot of attention to the architecturally exposed structural steel quality, because the beauty of the shell comes from the form, the smoothness of the form, the sharpness of the edges. And so with that, we looked at a variety of shell forms, and what you see highlighted there was the form that we eventually settled in on. Okay, next slide. So the basic premise was basically a circular cylindrical shell that would be perforated. The idea was to use sort of laser cutting to be able to put in a series of openings that, again, give it some lightness, allow light to penetrate inside and give it a bit of character. But really, when you look at the shell, it's really functioning as a traditional arch, where you have the arch, basically each side forming an arch, carrying the forces across the abutments with the tie girder down along the deck level, and then the vertical sections generally acting as ties to hang the deck loads up to the arch. So we started with that form and then looked at a Voronoi pattern as a starting point. And you can see there the red colored image, various random patterns, but those openings are tighter in the area where you have the arch forces, again, to try to reflect the fact that that's where the main forces are being carried, and therefore we need more material in those locations. Next slide, please. So we had a series of meetings with the Waterfront Toronto Design Review Panel, and starting with that form that we were just looking at, they encouraged us to make the bridge more transparent, to open it up more to the views of the river and the park and the community. And so also they suggested that we try to minimize the amount of material to more clearly illustrate the flow of the forces in the structure. And so with that, we went from the openings, the random openings that we were showing there, the Voronoi pattern, into a more open look where we started to cut away more material and had a series of essentially ribs that were the hangers that hang the forces up from the deck up to the arch component of the shell, and retain that center dome section to try to stabilize the two sides of the shell. So it's still that circular form, but in a more open type of view. Next slide, please. So this kind of illustrates the development. So we started with that circular shell, perforated circular cylindrical shell, I should say, pattern, and then opening it up a little bit further. And still, we wanted to make that look even a little bit more elegant. So we started to remove even more of the hangers to open it up further, and we started to sculpt the arch sections of the shell in order to make it a more interesting form. So if you go to the next slide, please. And this is where we wound up, and this is what you're seeing now is being constructed. So the arch sections of the form are a little bit more sculpted. There's fewer hangers to open up the interior sections. And we also introduced the use of colors. So the idea was to use strong colors on the interior. There's two things, because each of the bridge sites will have a different color. So each one has its own character, but at the same time, it really helps to highlight the structural form of the shell, which is gives it that sort of unique shape and really brings it to be more prominent. So with that, I'm going to turn it over now to Jonathan Werner, who will take you through the technical aspects of the design.
Yes, so I'm just going to run through the structural design and some of the dimensions of the bridge. The LRT bridge is the first of the four Portland's bridges, but it's also the smallest, with a span of approximately 56 meters, about 14 meters wide, and an overall height of approximately 10 meters. It's been designed to function as either a BRT or an LRT bridge, so a bus rapid transit bridge or an LRT bridge. So there's two different loading regimes that we had to design for, including for the LRT. You have to design for an additional concrete overlay on top of the deck. Next slide, please. So here you see the overall form of the structural steel in a perspective view. The bridge functions, as Mike mentioned, as a tied arch bridge with steel plate hangers connected to the tie girders at the same locations as the deck beams. The deck beams are variable depth steel eye girder sections with welded studs to make it composite with the poured in place concrete deck. They're variable depths since we account for the cross fall of the deck with the variable height of the deck beams. The tie girders are closed boxes with vertical internal stiffeners at each deck beam location, which also coincides with the arch hangers. The aesthetic form of the bridge is dictated welded constructions, which led to significant fatigue design considerations, especially for the tie girders, which are fracture critical elements. The arch legs and the shell dome are all open sections constructed of welded steel plates, which have been bent in double curvature. The cantilevered sidewalks have been designed using an orthotropic steel deck section. So thinking on the structural as a structural system here, loads on the decks come from the composite concrete deck into the deck beams, which transfer to the tie girders, and then because of the hangers being in the same location or along the same grid line as the deck beams, that is transferred directly through the hangers into the arch. And the reason for this is really to minimize bending within the tie girder and keep it primarily as a tension element. Next slide, please. So as I mentioned, the legs are open sections, but they're also non-prismatic open sections. If you look at the top right of the slide, the area that's been shaded in orange in the detail shows this open section at one location. However, and Fitzgerald, if you wouldn't mind just playing the video. As you'll see in the video here, that the open section and the shape of that changes throughout the arch. So we had to account for that within our analysis. So this required quite a bit of detailed finite element analysis, including considerations of local and plate buckling and member buckling, as well as initial imperfections and section capacity reductions due to residual stresses. Next slide, please. So the overall form of the arch and the shell elements, it's difficult to describe in 2 dimensions and really has to be described in 3 dimensions. And this was done through the creation of a Rhino model. And that was the basis of both our design drawings and our analysis. Meshing these elements directly into SAP was not efficient, so we wrote algorithms in Grasshopper to mesh these elements and then transferred them directly to CSI Bridge. This allowed for a lot of flexibility since we were able to change parameters in the algorithm to adjust mesh density locally or globally within the model as needed. Next slide, please. This gives an example of some of that flexibility created through Grasshopper. This slide we're talking about the parametric design and modeling. The cantilever sidewalks on the bridge are quite wide relative to the deck width, and this is actually one of the narrowest sidewalk. On the others are even wider. It's also the narrowest deck though too. But the reason for this is to accommodate significant public realm aspects of the overall project for pedestrians as well as bicyclists. To reduce the weight of these sidewalks, it was decided to use an orthotropic steel deck. We do have a concrete overlay or asphalt overlay in some places, depending whether it's bike or pedestrian access. to help adjust the variable widths of the sidewalks and to optimize the orthotropic steel deck ribs, we set up a grasshopper algorithm to give us flexibility to make these adjustments. Fitzgerald, if you wouldn't mind playing the video, then I'll show you some of that flexibility. So we set up a number of parameters, rib heights, rib spacing, length of cantilever, and we're able to adjust those and mesh as we need to. There were some adjustments during the project to sidewalk widths, and this helped us to adjust to that, as well as to really come up with the best spacing for the ribs and for the height of the ribs as well. Okay, next slide, please. So the hanger welding sequence, this is something that came up during fabrication. Cherubini had noted that welding the initial hangers was fine, but once you started to, once you welded the next set of hangers, what was happening was the weld shrinkage would lead to the initially welded hangers to go into compression and start to buckle. So in collaboration with Elliston and Cherubini and Harborside, we met to discuss a variety of options for sequencing this work. Cherubini also completed a series of weld tests in their shop to measure the approximate weld shrinkage for us to use in our finite element analysis. One of the chief challenges here is that the hangers are actually quite slender, and so have to be kept in either tension or very low compression throughout. So after a lot of brainstorming and FEA analysis, we arrived at a detailed sequence, which involves simultaneous welding of hangers in groups of up to 4, as well as heating of hangers that had been previously welded to protect them from going into tension and to buckling. To measure the strains in the hangers, Harborside also developed and implemented a monitoring plan using strain gauges on the hangers. Blair from Cherubini is also going to discuss the implementation of the sequence in more detail in his form of the presentation. Next slide, please. So as previously mentioned, the architecturally exposed structural steel was an important component of this project. We arrived at AESS 3 for above the deck, which is quite a high level of AESS. This only goes up to 4, and 1 and 2 below, where the elements were of less importance. Above the deck, you're primarily looking at the shell and the arch aspects. We used CSCE guidelines for AESS as part of the contract. And so, of course, the major challenge of this is achieving that required aesthetic requirements for the AESS with heavy steel welded elements. So to help deal with this ahead of time, we added in a mock-ups into the work that Cherubini completed prior to bridge fabrication. And the final agreed upon mock-ups, as you can see in the picture here, there's 5 different mock-ups showing different aspects and portions of the bridge. So the final agreed upon mock-ups in combination with our discussions and comments were then used as the standard for achieving the AESS levels and finishes. Next slide, please. And my last slide is just wanted to discuss the structural steel coating and durability aspects. In general, we're using the MTO 3-coat system, which is an epoxy, zinc, epoxy, polyurethane coating system. And it's the Acrylon system by Sherwin-Williams. However, for some elements, such as the tie girders and hangers, metallizing was also used as the base coat. And this is really to protect these fracture critical and primary tension members that are heavily exposed to chloride spray. And with that, I will hand off the presentation to Blair, I believe.
Thanks, Jonathan. We're having a little bit of a storm out here. I've had power flickers that have kicked me off 3 times so far. I've switched over to a hotspot on my cell phone, so hopefully I can get through this here. If not, Robbie, could you carry on for me? Next slide, please. So as Jonathan described earlier, when we came to look at this as a fabricator, we broke it down into much the same components as he's described: the tie girders, the arches, the domes, the orthotropic sidewalk, and the deck beams. And really, we did that to be able to generate as many different work faces as we could to meet the schedule that's required for this project. The challenging part of this project really, when we looked at this, when it went from a circular curved surface to sort of a 1D curve or a 2D curve to a 3D curve, where you've got steel shaped in 2 directions. Next slide. So this beautiful shape was modeled in 3D, and we had 5 different groups working on this project. And of course, we had 5 different 3D modeling packages that we were all trying to get to work together. Eventually, we arrived at the sort of the IFC model to be able to move things fairly effectively from one model to another, not with, or from one modeling package to the other, not without its challenges, but it seems to work fairly well now. Next slide, please. So as I said, the change from a cylindrical curved surface to a 3D curved surface was something that we don't do in-house, or the 3D forming we don't do in-house. So we actually partnered with a company called CIG Architecture, who is spawned from the shipbuilding industry. And they specialize in 3D forming for architectural projects. And you can see that they're forming some fairly heavy plate, maybe not quite as heavy as some of the pieces we have on this project, but with a large press. And they're in the Netherlands, but they've done an excellent job. Next, please. So as I said, we broke down the project down into its segments, or its components, and you can see in the picture on the left some of the arch legs that have been fit up and are being welded now. We welded with submerged arc to the largest extent possible. There's a lot of heavy full penetration welds. We've got material as thick as 125 millimeters on this job, but the arches and domes are up to 80 millimeters. And so depositing metal quickly, evenly, and in a controlled manner is really important, and subarc gives us that control. You can see in the picture on the right-hand side, it's the dome that's been fit together and welded, and it's upside down. And we chose to do it in the upside down position because it's the AESS requirements on this project meant all the welds on that dome and the arches needed to be ground smooth, and we wanted to eliminate any overhead grinding. So we welded it and ground the inside of that dome in that position upside down, and then we'd flip it and finish the grinding on the outside of the dome afterwards. Next slide, please. So as Jonathan and Michael described, the aesthetics are very important in this project. And we talked about different ways of handling the coatings and perhaps pre-painting some pieces before they got assembled. But at the end of the day, we decided that it was just too important, and we constructed a coatings facility there. You can see it's a large tent structure, so that we could paint the whole bridge all in one go. So it's metallized, it's blasted, metallized, primed, intermediate coat, and top coated all in one go, rather than piecemeal. Next, please. This is just a little time lapse video. They're kind of fun to watch. So we'll cut it off around the 1 minute mark, though, if you could, Fitzgerald. Perfect, thank you. You can go to the next slide. I wish the painting process went that fast. So Jonathan talked a little bit, or talked about the challenge we had with the distortion we initially saw in the hangers, the buckling of the hangers. So the problem, you'd weld, say, a pair of hangers, and then when you went to weld the adjacent ones, when those welds cooled, they would shrink and put the ones that you had previously welded into compression. So as I said, we worked out, between the whole team, we worked out a sequence of welding. So where we would weld, we were actually welding 4 hangers simultaneously, the 4 middle hangers simultaneously. And we actually had welders set up, and we were starting and stopping passes at exactly the same time, flipping side to side on the weld at the same time, just to make sure that we were balancing the forces in that weld. And we were carefully controlling the preheat. And then when we would move to the next set of hangers, so outside of the 4 that we had just welded, we would actually preheat the 4 that had been welded to grow them the same amount that the ones we were currently welding would shrink, so that when everything cooled, they would shrink the same amount, resulting in maintaining tension or very, very low compression in those hangers. So it was an interesting challenge, and it's working very well. Next slide, please. So one of the most, the other interesting aspect of this was putting together the dome, and I showed some of the forming that CIG was doing, and they've done an excellent job making these pieces so they fit nicely. You can imagine if they weren't done well, how much trouble you'd have fitting these together, but they did a great job. And with the dome, with the mold frame that you see in the top right-hand corner, we're able to set all the plates in and tack them together, working progressively from the middle out, just to make sure everything fits together nicely. And then carefully sequencing our welding and back gouging and monitoring the dome shape, with total station equipment, just to know if things are starting to pull one way or another, and then adjusting the welding as you go, and sometimes having to reposition a piece just to make sure that by the time you make it out to the ends where the arches connect, that everything's in the right location. It's all a kind of a careful balancing act, but it seems to be working quite well. Not without its challenges, though. Next slide, please. So yeah, just a quick note on the AESS, the architecturally exposed structural steel, and trying to conceal all the welds and having all these 3D curve shapes meeting. We learned a fair bit about what makes it easier, what makes it really difficult to do that. So definitely the fit up is key, and you would rather have a high section that could be ground rather than creating a low that has to be filled and then ground. Usually that has to be blended out a long, long way, where a high can be concealed by grinding fairly easily. The other thing is having nice, consistent welds, like you can see in that sort of top middle picture there, giving, it gives you a better chance to grind uniformly to conceal that weld. And then the other two things are being careful not to overgrind, because that shows up, sticks out like a sore thumb once you get some paint on it. Eliminating the overhead grinding, which we did on the domes, and then actually right down to training on grinding techniques and proper ergonomics, because we have people doing this grinding, running a 7-inch grinder for 8 hours a day. So proper technique, micro breaks, proper positioning, all that are absolutely important to keep those people healthy. Next slide. So I'll turn it over to Robbie here.
Thanks, Blair. Yeah, we are having a good nor'easter here in Nova Scotia. So if you hear I'm in my house, so if you hear the wind blowing, I'm not outside, I swear. We'll go through the installation. In addition, Harborside were tasked with doing all the temporary works in the shop, all the frames that Blair showed, all the geometry control. And then what I'm going to go through here is go through our process of moving the structure around the yard, in and out of the plank shed, get it ready for loading on the barge, and all the temporary works that are involved for the barge transport, and then the erection on site in Toronto. So next slide. So first, going through all the temporary works we had to use. The first you can see 2 plate girders that are not nicely painted below the structure. We called those the transfer beams, and they're tied together with diaphragms at intermediate points. And those transfer beams are really necessary because we are going to spin the structure 90 degrees to the barge when we get to Toronto, because the barge can't fit in the Keating channel except for parallel to the channel axes. And we need to spin the barge 90 degrees to get it parallel to its span. That ends up being, with the barge width and the ability to spin it, we end up with about a 17-meter cantilever from the end of the arch structure, where its bearing points are, to the center of what we call the turntable on the barge. We looked at beefing up the tension ties to accommodate this, but it just didn't make sense from a design perspective, and the inertia and amount of steel we needed to do that. Coupled with that, this process is being used for both Cherry Street North bridges, the LRT bridge and the heavier vehicular bridge that is set to be erected in the end of 2021. So it actually, from an efficiency point of view, made sense to create that out of temporary steel rather than beefing up 4 sets of tension ties to handle the erection conditions as well as the in-service conditions. So what you see in the foreground is the smaller non-sidewalk transfer beam, and that is an 1800 deep plate girder. On the sidewalk side with the heavier loads, we have a 2400 deep transfer beam, and that's really for when it's in the cantilevered condition. Underneath in the middle, you can see a structure that is on the ground. That is the turntable that we'll get into momentarily to show you how we spun or turn the structure and the transfer beams 90 degrees relative to the barge. Next slide. So here is a cross section to the left of the transfer beams, and you can see the typical diaphragms that are tying the 2 beams together and helping create stability. In addition, you see these bumper assemblies, and these bumper assemblies bump up against the side of the tension tie bottom flange. And what that does is it's multifold. First, we have two very flexible plate girders that are not tied together with in-plan bracing to try and minimize things to deal with on site and to minimize weight as well. So instead, even though the transfer beams are supporting the superstructure, the arch superstructure from a gravity perspective, laterally to avoid lateral torsional buckling and to laterally support the compression flange of the transfer girders, the bumpers are acting through the steel superstructure. The steel superstructure is actually supporting the transfer beams below laterally. Also at the load points, whether it be SPMTs during the loading process of the barge, on the barge, or during the turning operation, all wind loads are taken out through these bumpers and back down through the supports, whether they be the supports be on the turntable or, as I mentioned before, the SPMTs during loading of the barge, or during barge transport where we have end blocking at the ends of the structure. To the right, you can see the turntable and how it fits onto the barge. The Glovertown Spirit barge is going to be used for all four of these structures from McKeel. The barge deck was never designed to handle concentrated loads such as this, more of a uniform load kind of uniform pressure on the deck structure. So we had to do advanced FE modeling and a little bit of reinforcing to the deck of the barge to safely resist and transfer the concentrated loads from the structure, from the launch structure. So we are dealing with loads that are on the order of 346 tons for the superstructure. The vehicular one, just so you know, the heavier one that it's actually designed for is going to be 450 metric tons. The transfer beams weigh about 164 tons, and the turntable is another 68 tons. The turntable diameter, as you can see, is almost the width of the barge. It's just over 22 meters in diameter. Next slide. So here you can see some pictures of the turntable and the transfer beams above. You can see the bracing in the left-hand side picture. That is really the transport bracing, because as you'll see, when we take it out of the yard and load the barge, we basically carry the turntable as well underneath the structure and pick that up in the air. And the SPMTs carry the superstructure, which is supported by the transfer beams, and the transfer beams are also supporting and dragging along or hauling along the turntable as well. When we get to the barge, we lower the SPMTs to put the turntable onto the barge, and then get rid of that bracing and put on the C lashing for transport afterwards. In the right-hand picture, you can see the smaller non-sidewalk transfer beam above and the 150-ton radial rollers below. On the sidewalk side, the heavier load side, we have 300-ton radial Hillman rollers to transfer the load, to basically allow the rotation of the structure, transfer the load back to the outrigger positions that bypass the deck locally and get it into the stronger diaphragm sections of the barge structure below. Next slide. So here's a picture of the end blocking, and the end blocking is really at the end of the transfer beams, which is effectively the end of the structure, superstructure above, and the end blocking is present for transport conditions on the barge. So when we take the structure out of the yard, go over what we're going to go through the jump bridge, and then we lower with SPMTs, and then we lower the SPMTs with their stroke capabilities directly onto the end blocking assemblies at the four corners, and then put C lashing on or bracing on to keep the structure stable during very large potential storm events during transport from Dartmouth to Toronto. Then when we get to Toronto, we jack at the end blocking conditions. You can see the stiffener to the left-hand side of the stool. We jack there, kick the stool out, transfer the loads to the turntable, and then we're in the right condition then to spin the structure parallel to its span and just hovering over its permanent foundations. Next slide. So because Cherubini's quayside facility in Dartmouth is on the Halifax Harbor, and we have to deal with tides, and we also have to deal with the articulations or slope transitions coming off the approaches onto the jump bridge and then onto the barge, which also has, as the load comes on, it lists and it basically it's freeboard and draft changes. Hence, we call this a dynamic loading operation. We had to design a jump bridge. Now, the jump bridge was mainly to mitigate the transition angles and to deal with tidal conditions in the Halifax Harbor during the loading process, but it was also to mitigate or reduce lateral surcharging effects on Cherubini's existing quayside wharf structure. Next slide. So once we had it loaded, you can see on the barge, you can see in the foreground the transfer beams supporting the steel superstructure above, and then transferring this load directly down to the end blocking on the barge. Also, you can see in the middle the turntable, so that when we get to Toronto and jack from the end blocking, lower down, deal with the cantilever deflections. Then we transfer the load to the turntable to facilitate the spinning of the structure relative to the barge. We also see all the bracing around, and that is based on a sea lashing to keep the structure stable on the barge during designed storm conditions during transport of the barge from Dartmouth, Nova Scotia to Toronto Harbor. Next slide, please. When we get, this is the last piece of temporary works, and then we'll get into the meat of going through the transport and erection procedure. These are the erection temporary jack down frames that are located on the permanent abutments. There's 4 frames total, 2 on each abutment, that when the structure gets to Toronto, is spun 90 degrees, so it's hovering over its permanent supports. The barge is ballasted as much as we can. The barge is ballasted to a freeboard of 3 foot 3 inches. That's the minimum legal freeboard we can handle. At that point, the structure is still elevated over the beam seats, or the final elevation of the structure, by approximately 6 feet. So a jack down procedure from underneath with jacking and blocking didn't make sense. So we designed erection jack down frames that were hanger assemblies to allow us, with hollow core jacks and restroking areas, to allow us to rapidly and in a controlled manner jack the structure down onto the permanent bearings at the end of the erection procedure. Now, one thing that came up is that the bearings, the permanent pop bearings, because of COVID, were late getting to site. In fact, they were almost 2 months later than when the erection was completed. That, coupled with the fact that we didn't want to leave the structure on the jack down frame hanger assemblies for 2 months because they could only handle certain storm events, we decided, you'll see in the pictures, we decided to use temporary bearing blocks to set the structure on, concrete blocks and steel plates above, and then put the hanger frames in, pick it up off the blocks, take the blocks out longitudinally onto the approaches, and then lower it onto the bearings when the bearings came. That all stemmed from some delays in getting the bearings that was blamed on the current pandemic. Next slide. So you can see here, this is what I was just talking about. You can see the 4, or the 2 in the foreground, the 2 in the background, the 4 hanger frames ready and installed. And you can see the temporary bearing blocks we put in place until we get the bearing assemblies. Now, next week, the jack down assemblies are going to pick the structure up just enough to relieve the load off the bearing blocks. We're going to pull the bearing block assemblies out longitudinally onto the approaches, and then lower under a controlled manner the structure about 6 feet onto the permanent bearing assemblies. Next slide. So now we're getting into the transportation and erection. So this will go quick now that you know what all the temporary works are. So you can see we've taken the structure out of the paint shed. So one of Blair's last slides there showing it being painted in the coated in the paint shed, and we've put it on concrete blocks temporarily so that we could remove the SBMTs from underneath the structure. Then the SBMTs go out in the yard, go underneath the transfer beams that were blocked temporarily in the yard, and pick up the transfer beams and the turntable that is temporarily strapped for transport to the underside of the transfer beams. Then with the transfer beams and turntable supported by the SBMTs, the cranes, R&D cranes, which is also owned by Cherubini Metalworks, 4 cranes were put, 1 in each corner, to pick up the superstructure to allow us to slide the SBMTs and transfer beams underneath the structure and then lower it under control onto its support positions on the top of the transfer beams. With that in place, we were ready then to take the transporters and this superstructure and the transfer beams and the turntable over to the jump bridge to start loading with the loading over the jump bridge and onto the barge. Sorry. Next slide, please. So here you can see it with the SBMTs supporting the transfer beams and the transfer beams in kind supporting the steel superstructure above and the turntable below, transitioning over the jump bridge assembly. Next slide. This is near the end of the SBMT loading of the structure onto the barge, so it's getting into position relative to the end blocks. The end blocks are slid into place, and then the SBMTs are stroked down with their hydraulic capabilities to transfer the load from the SBMTs to the end blocking. The stern end SBMTs were then able to get off the barge basically with the reverse route that it took to load the barge over the jump bridge. The SBMTs on the bow end of the barge were removed later when the barge was turned 90 degrees relative to Cherubini's wharf to install the sea lashing, and they were removed off the barge with Cherubini's cranes. Next slide. So here's another picture just when the leading SBMTs are reaching the stern of the barge. Under that load condition, the barge listed about 2.5 feet. So the draft increased at the stern end, by about 2.5 feet relative to the bow end. So it just tells you the degree of load and the amount of influence that had on the loading of the barge and making sure that the transition angles and the tides were right to allow the SBMTs to transfer the load across the approaches, over the jump bridge, and onto the barge structure. Next slide. Here we are with the barge turned 90 degrees, as I mentioned, with all the SBMTs removed, and we're just getting ready here, doing the final touches of putting the sea lashing in place in preparation for the voyage to Toronto Harbor. Next slide. So here's the route the barge took. So it left Halifax Harbor. It went north and east up the coast of Nova Scotia, across west, then effectively through the Canso Strait and the Canso Causeway, and then down through the Northumberland Strait up into the Gulf of St. Lawrence, and down through the Seaway, St. Lawrence Seaway, through the locks, and then down into Toronto Harbor and into the Keating Channel at its final destination. Next slide, please. So here we are, a little video here of when the barge gets to the Keating Channel, you can see we transferred the loads from the end blocks, then spun the bridge 90 degrees. That took about 20 minutes on the turntable, ballasted the barge to transfer the loads from the barge to the end blocking, then spun the transfer beams back 90 degrees to be parallel to the barge, and then removed the barge from the site. And that's how you see the structure today, except with the hanger frames now in place at each end, in preparation to remove the temporary bearing blocks, lower the structure down onto the permanent bearings. You can also see to the left-hand side or to the east where the adjacent vehicular bridge is going to be erected later in 2021. It will be erected effectively in the same manner as you see the LRT bridge was completed. Next slide. So we'll just go through this quickly. You can see I talked about the end blocking and removing the lashing when we get to site and all the rest. So first thing when we get to the Keating Channel in the final position was to remove all the C lashing. Then what we did was put jacks under the jacking points at the end blocks, jack the structure up, remove the end blocks on top of the end supports, the barge supports, and then lowered the thing to allow them to allow it to transfer from a simple span supported at the ends to a cantilevered structure supported at the turntable roller positions. Next slide. So here you can see the structure completely supported on the turntable, which is again supported on the barge deck, and we're in the process of spinning the structure 90 degrees to be hovering over the permanent abutments. The spinning process was done with bulldozers on site and wire rope leads, and took very little load because we had new Hillman rollers. The friction on those rollers was seen to be less than 1%. So very, very easy to spin the structure into place, and that was done, as I mentioned, in about 20 minutes from start to finish. Next slide. So another couple pictures of the rotation of the bridge 90 degrees relative to the barge, and you can see the lead line there in the right-hand picture of the dozer wire rope line to spin the structure. So we had 4 dozers. Some of the dozers were there, bulldozers were there also to provide temporary mooring lines, mooring points to the barge in the Keating Channel. And then we used diagonal dozers first, say the first 2 dozers opposite corners for the first 17 degrees of the spin. Then we switched to the alternate 2 dozers to complete the 90-degree rotation. Next slide. There's the bridge in the final position, but still, and the barge ballasted as low as it can go, but still supported on the transfer beam. So we're just lowering it just a little bit more to transfer the load from the barge and transfer beams to the temporary end blocks. Next slide. Here we are with the load fully transferred to the end blocks now, so there's no more load on the transfer beams. The bumpers that we mentioned earlier in the presentation have been removed, and the transfer beams have been rotated back 90 degrees relative to the structure or parallel to the barge in preparation for the barge to leave the site and go back to Dartmouth, Nova Scotia. Next slide. And there you have it, just before the barge leaves the site, the bridge on the temporary end blocks. Next slide. And as I mentioned before, the jack down frames are now installed, and we're scheduled for next week to jack the structure up, to remove the load from the bearing blocks, temporary bearing blocks, remove the bearing blocks, and then under control and level, in a level manner, lower the structure using the hanger frames onto the permanent bearings.